In this lecture, we're going to study ocean currents from a physics perspective. The focus will not just be descriptive, but to understand the forces and mechanisms that drive motion in the oceans. We will connect fluid dynamics, Earth's rotation, and thermodynamics to explain how ocean water moves at both surface and deep levels. These learning objectives define what we aim to achieve by the end of this lecture. We will understand what ocean currents are and why they are important in regulating Earth's climate. We will identify different types of currents, including surface and deep currents. We will study the physical forces governing ocean motion, especially pressure gradient and Coriolis force. Then we will move toward wind-driven circulation, Ekman transport, and thermohaline circulation. Finally, we will connect all these processes to global heat transport and climate regulation. The book shown here is our reference, which covers these topics in a structured way. In the previous lecture, we discussed heat transfer in oceans and thermohaline circulation. Temperature and salinity variations create density differences in seawater. Now, whenever density is not uniform, the system becomes unstable and motion begins. This is the key idea. Density gradients lead to fluid motion. So now we shift from heat transfer to fluid dynamics. Ocean currents are simply the large-scale response of seawater to these physical imbalances. Ocean currents are continuous and directed flows of seawater. From a figure, you can clearly see arrows showing different current paths across the globe. These arrows represent both direction and relative strength. Notice that warm currents are generally shown in one color and cold currents in another. This tells us that currents are also transporting heat. So ocean currents are not just motion, they are energy transport systems. They move heat, salt, and momentum across the Earth and play a central role in climate regulation. This slide combines two important ideas. First, types of currents. Surface currents are mainly driven by wind and Earth's rotation. Deep currents are driven by density differences. The diagram on the right clearly separates surface and deep circulation, showing how they form a connected system. Second, forces acting on ocean water. The pressure gradient force arises due to differences in sea surface height. Coriolis force deflects motion due to Earth's rotation. Friction acts near the surface due to wind interaction. Gravity maintains vertical balance. The figure showing global currents helps visualize how these forces combine to produce organized patterns. Now we come to the pressure gradient force, which is the fundamental force that initiates motion in both the atmosphere and the ocean. Let us understand this using the figure shown here. The diagram represents a coastal region and shows two situations, daytime and nighttime. It is not only illustrating pressure gradient in water, but also the thermal contrast between land and sea, which is very important physically. During the day, land heats up faster than the ocean. This happens because land has lower heat capacity, while seawater has higher heat capacity and can absorb more energy without a large increase in temperature. As a result, the land becomes warmer than the sea. The air above the land gets heated, expands, and rises, creating a low-pressure region over land. At the same time, the air over the ocean remains relatively cooler and denser, forming a high-pressure region. Now, due to this pressure difference, air moves from the sea toward the land. This is known as sea breeze. At night, the situation reverses. Land cools faster than the ocean. Now the ocean remains relatively warmer, and the air above it rises, creating a low-pressure region over the sea. The land becomes cooler, forming a high-pressure region. So the wind direction reverses and flows from land towards sea. This is called land breeze. Now, the key idea is that this differential heating creates pressure differences. And wherever there is a pressure difference, motion will occur. In the ocean, Even a very small slope in sea surface height or slight density variation produces a pressure gradient. This pressure gradient drives the movement of seawater from high pressure to low pressure. The mathematical expression shown here tells us that the force depends on how pressure changes in space, and the negative sign indicates motion toward lower pressure. So this figure beautifully connects thermal properties of land and water, creation of pressure differences, and the resulting motion driven by the pressure gradient force. This is the starting point of all large-scale ocean currents. Once water starts moving, Earth's rotation changes its path. From the figure, observe how motion curves instead of remaining straight. This is due to the Coriolis effect. In the northern hemisphere, motion is deflected to the right. In the southern hemisphere, it is deflected to the left. The diagram clearly shows Earth's rotation and how moving objects change direction relative to the surface. Physically, this happens because we are observing motion in a rotating frame of reference. Now, an important balance forms between two forces. The pressure gradient force tries to move water directly downhill, while the Coriolis force deflects it sideways. When these two forces balance, the water no longer moves toward low pressure, but instead flows parallel to pressure contours. In the figure, you see circular flow around a high-pressure region. The arrows show that water is not moving inward or outward, but around the system. This is called geostrophic flow, and it explains the stability of large-scale ocean currents. Wind plays a major role in driving surface currents. From the diagram, you can see global wind belts such as trade winds and westerlies. These winds transfer momentum to the ocean surface. This generates movement of water, forming large circulation patterns. The second diagram shows how these wind belts are arranged with latitude, helping to understand why currents form specific global patterns. So atmospheric circulation directly controls ocean circulation at the surface. Now look at how wind affects water with depth. The figure shows a spiral structure. The surface layer moves in one direction, but deeper layers are progressively deflected. This creates the Ekman spiral. The most important concept is that the net movement of water is perpendicular to the wind direction. So even though wind blows in one direction, water transport occurs sideways. This is a purely rotational effect caused by Coriolis force acting layer by layer. From the figure, you can see large circular patterns in the oceans. These are called gyres. They form due to the combined effects of wind, Coriolis force, and continental boundaries. In the northern hemisphere, the rotation is clockwise. In the southern hemisphere, it is anti-clockwise. These gyres organize ocean circulation into large, stable systems. Now observe the Gulf Stream in the figure. It is a strong, narrow current located on the western side of the Atlantic Ocean. These currents are fast and deep, carrying warm water toward higher latitudes. The diagram shows how concentrated and directed this flow is. Physically, this happens due to the strengthening of flow on western boundaries, a result of Earth's rotation and conservation of momentum. In contrast, eastern boundary currents are broad and slow. The figure compares two regions, highlighting the difference. These currents carry cold water toward the equator and are often associated with upwelling. So here we see asymmetry in ocean circulation, strong currents on one side, weak on the other. Now, look at vertical motion. In the figure, surface water is moving away from the coast. This creates a gap, and deeper water rises to fill it. This is upwelling. This rising water is cold and rich in nutrients, which is why these regions are biologically productive. Downwelling is the opposite process, where water sinks. So ocean motion is not only horizontal, but also vertical. This slide connects back to density-driven motion. Cold and salty water becomes dense and sinks, while warm water rises. The figure shows surface and deep currents forming a global loop, often called a conveyor belt. This is a slow but powerful system connecting all oceans. It plays a key role in long-term climate regulation. From the figure, you can see warm and cold currents transporting heat across the globe. Warm water moves toward poles, and cold water returns toward the equator. This heat redistribution prevents extreme temperature differences on Earth. Ocean currents also influence weather patterns, rainfall, and monsoon systems. So oceans act as a global climate regulator. Ocean currents arise due to forces and density differences. Pressure gradient and Coriolis force control motion. Wind drives surface currents, while density drives deep circulation. Together, these processes form a global system essential for Earth's climate. These questions are designed to test your conceptual understanding. Focus on explaining mechanisms rather than memorizing definitions. Use diagrams for Coriolis effect and Ekman transport. The derivation of pressure gradient force should be understood physically, not just mathematically. This concludes the lecture. Thank you for your attention.